Problem 1A asks us to show the steps of running Quicksort on the list below, always selecting the first item as the pivot and using three-way partitioning. So we're going to run Quicksort using that simple 3-scan partitioning method we just went over, and we're going to select the first item as the pivot. So taking a moment, what's the pivot right now? Well, it's the first item, so that's going to be 18. Now our task is to do 3 scans over the list, first putting in the things less than the pivot, then the things equal, and then the things greater. So right now we need to find every item that is less than 18. That's going to be these 3. So we put them in. And now we have filled it up to here. And so from this point on, we can start putting the things equal to the pivot. And that'll be the 2 18s. Finally, starting from the remaining empty portions of the array, we can put in the items greater than the pivot. And so that'll be 22, 34, and 99. So you can see that we've successfully partitioned around the pivot 18. And now we have these subarrays on the left and right. So are we done running Quicksort? Well, not quite, right? This array definitely isn't sorted yet. And the idea is that we have to recursively call on these left portions and these right portions. The key thing to notice, though, is that the pivots are actually in, or the things equal to the pivot are in the correct place right now. Because, I guess, logically thinking about it, if we knew 3 items were less than 18 and 3 items were greater than the 18s, well then, no matter what ordering happens here, we don't know yet, but it could be anything. There's so many options, but regardless of what happens there, these 18s are going to be in the next spot because everything to the left is less and everything to the right is greater. So again, no matter what ordering you put things in, 18s will be in the middle. And so 18s, or the things equal to the pivot, are now in their correct place in doing this 3-scan partitioning. But we still have to do the left and right subarrays, so we're going to do a recursive call to Quicksort right here. So let's do a recursive call on the left side. Well, again, what's our pivot? We're selecting the first item as the pivot here, and so we'll pick 7. Now the question is, what comes next? We're doing 3-scan partitioning, so we have to do 3 scans of the array. First looking for things less than the pivot, then equal, then greater. And we're looking at this recursive call, right? So first, we're going to put in 4. Then we need to do things equal to 7, so that'll just be 7. And finally, we're going to call on things greater than 7, which is 11. And so then, under the hood, we'd be doing some more recursive calls here, right? But then presumably we have this recursive base case in Quicksort, which says when the array is of size 1, then just return. So this recursive call is kind of completed. We've completed this whole recursive call. Now take a moment and think, do we need to recursively call Quicksort on this portion of the subarray? No, we don't, right? Because as we said earlier, we know that the 18s are in the correct place. We're only calling our Quicksort on the left and right subarrays, or the things less than the pivot and the things greater than the pivot. Everything in the middle, they're all equal to each other because these were all the items equal to the pivot. And so there's no need to do any sorting amongst these because everything in this little middle section is equal to each other. And so we would have never made that recursive call there. We just know that they're in the correct place. But we still have to do the recursive call on those things greater, right? So we're going to go ahead and do this, and we select 22 as our pivot. And take a moment and think, what happens here? Well, we do a scan for things less than the pivot, but in the subarray, there's actually nothing. So then we do a scan for things equal to the pivot, and we fill that in. Finally, we do a scan on things greater than the pivot. And what comes next? Well, normally we'd be doing a recursive call on the things less than the pivot and the things greater. But since there's nothing less than the pivot, we're just going to go ahead and do it for the things greater. So we do another recursive call to Quicksort. Here we're going to select the pivot as 34. And then what happens next? Once again, we're going to look for things less than the pivot, but there's nothing there. And so we just put in 34. And then we're going to look for things greater than the pivot until we fill in 99. And once again, we have reached this base case where, our subarrays that we're calling it on are of size 1, or in this case, there's actually nothing there. And so Quicksort is going to have some sort of base case that says, once you're size 1, we're done. And with that, we have completed all of our recursive calls, and we have sorted the whole array. So you just saw how Quicksort works with 3-scan partitioning. Super cool. The next part of this question asks, what is the best and worst case running time of Quicksort with Hoare partitioning on n elements? Given 2 lists, 4, 4, 4, 4, 4, and 1, 2, 3, 4, 5, assuming we pick the first element as the pivot every time, which list would give us the better runtime? So first, let's think, what's the best and worst case running time of Quicksort with Hoare partitioning? Well, the best case is going to be n log n. And I should say theta n log n. And this is because in the best case, we always pick, or we always perfectly divide our recursive subproblems in half. And so at the top level, we have the starting array. And the idea would be that we pick a pivot that partitions the array perfectly in half. And so this pivot is right here, and then everything on the one half is less than everything on one half is greater. In other words, we're picking the median as our pivot, right? And so then these perfectly divide in half as well, and so on and so forth, until we reach that base case we saw, where we have an array of size 1. Taking all of this together, we start with n elements, and at every level, we cut the array in half, right? Because we're looking at subproblems of half the size. And that means if we're on the xth level, we've multiplied by 1/2 x many times, because we're multiplying by 1/2 over and over. We have it every time. So how many levels does it take to reach the base case? Or in other words, what's the height of our recursive tree? Well, the base case is when we have 1 element. And now we can solve this equation. And so n times 1 over 2 to the x equals 1. You can move the 2 to the x to the other side and get n equals 2 to the x. And now we do some, log math, and we see that log base 2 of n equals x. So in other words, the height of our recursive tree is in log n. And what about the amount of work done at every level? Well, that's going to be n, because we're doing Hoare partitioning, which means we're walking those pointers from left to right. And that happens in every subproblem. But we can still see that the width of our tree, or in other words, the number of elements they're operating on, is summing up to n every time. So if the amount of work done at every layer of our recursive tree is n, and there are log n layers, then the total work is n log n. It's sort of multiplying like width by height to get an area, right? The total work. So what about the worst case? We just saw that the best case is when we perfectly split the array in half. Our pivot selection is chef's kiss, like down the middle, right? But what would happen if, let's say, we always picked our pivot to be, I don't know, the first or the last item in the sorted array, right? Well, then that's going to, instead of dividing the array in half every time, going to take your array and make it into the pivot and then everything else. And then the pivot and then everything else. And then the pivot and then everything else, and so on and so forth. Which means, well, before you were dividing the size of your subproblems in half every time. Now you're only subtracting 1. So how many layers is it going to take to reach the base case where your subproblems are size 1? Well, if you started with n and you're subtracting 1 for every layer, and you do this on all x layers, how long does it take to reach the base case of 1? That means x is roughly n, right? it takes pretty much n layers for us to reach the base case. So we have a recursive tree height of n, but we're still seeing roughly n elements at every layer. And so we have a worst case of n squared. Taking all this together then, of the two example arrays given, which one gives the best case runtime and which one gives the worst case? Well, if we're always picking the first element as the pivot, like we said, then 4, for example, every time is the median, right? This is actually a little tricky to understand, but 4 is the median of the array every time because all the elements are the median. So that means 4 is going to perfectly split this array into subproblems of 4, 4, and 4. The other way to think about this is that with core partitioning, your pointers will start at the ends, and we've said our pointers don't like equal items. So they start here and they go, oh, I don't like these, let's trade. And so they trade, even though nothing really matters, right? And once they trade, they move forward. And then they trade again, and then they trade again, and they do it evenly every time, so they meet perfectly in the middle, which means our subproblems are being divided perfectly down the middle as well. So if they're all the same, we see this best case runtime. On the other hand, if we have this sorted array and we're picking the first thing every time, we can see right away that this is going to divide our subproblem into the partition and then everything else, right? And at every level, we're just doing the partition versus everything else. And so this is exactly that worst case that we just talked about. So it's going to, we can say that this corresponds to the worst case. In other words, 4, 4, 4, 4, 4 happens to give us better runtime than 1, 2, 3, 4, 5 when we pick the first element as the pivot. Taking all of what we just did together then, what are two techniques that can be used to reduce the probability of Quicksort taking the worst case running time? So we just saw that when we have this sorted array and we pick the first thing as a pivot every time, we get this doo-doo n squared. What can we do to maybe prevent that? Take a moment to think about this one. And so hopefully you've thought about this for a moment, and now we're going to go over it. So as we just saw, one of the things that makes Quicksort take this n squared running time is if we happen to have a sorted array already and we're like picking our pivots poorly. So one thing we can do, oh, I just dropped my pencil. One thing we can do is shuffle the array. And if we randomize it, there's a super slim chance it's going to end up perfectly sorted again, right? The odds of that are just like crazy low if we shuffle this. So we can shuffle the list. The other thing we can do in a similar vein is to randomly select our pivot. Because here, as we just saw, if we're picking the first item as our pivot every time and the array is sorted, then we're going to end up getting that n squared runtime. Whereas if we had randomly picked the pivot, that actually might not have been a problem. So basically introducing randomness sort of evens out Quicksort, and we can sort of think about it in, I guess, a deep proof of Quicksort is very complicated, but the idea is that if we know the average case is taking n log n, to achieve that averageness and not end up in extreme cases, let's just shuffle everything and hope the randomness sort of even out the playing field. And so both of these techniques can help improve Quicksort. And that is all of problem 1.